Greetings to you. Welcome to Physics with Ben. Don't forget to like, subscribe, and share this video to those that need it. In today's video, we want to continue with the topic electric field 1, static electricity. Electric field 1. In this electric field 1, we want to look at capacitors. Capacitors and capacitance. This is a major topic. If you watch the other video I did on electric field 1, in that video we looked at what a field is. We defined a field as a region or a space around which the influence of some physical agents such as magnetic force, electric force, and gravitational force can be felt or experienced by an object placed in it. We looked at types of field and we said that we have scalar fields and vector fields. That scalar fields are those fields with only magnitude but no specified direction. While and the examples of scalar fields are heat energy or temperature, having just magnitude but no specified direction. And then examples of vector fields, we looked at gravitational field, electric field, and magnetic field. That vector fields are those fields that has both magnitude and also specified direction. We looked also at electric field. That electric field is a region or a space around which the influence of electrostatic force of attraction or repulsion can be felt or experienced by a charge placed in it. We looked at Coulomb's law, and we were able to state Coulomb's law as follows: that Coulomb's law states that the electrostatic force of attraction or repulsion between 2 point charges Q1, Q2 is directly proportional to the what? The product of the charges Q1 and Q2 are inversely proportional to the square of the distance between them. We looked at electric field intensity as E is equals to force all over charge, electric potential as V is equals to W all over Q. W all over Q. And so in today's video, we want to concentrate on electric field 1 and also capacitors. I would like you to go back to that video. That video is very, very rich. But that video on electric field, and Coulomb's law, watch it and then come back to this video. Don't forget to subscribe and share to those that need it. So let's begin. What do you mean by a capacitor? What do you mean by a capacitor? I believe you have seen this before. This is what a capacitor means. You can see what I'm holding in my hand is simply a capacitor. Another one is here. This is what we mean by a capacitor used in electronics. You can see you're having 400 volts and 47 microfarad. This is what a capacitor is. So we want to study the physics behind the behavior of this guy. What do you mean by a capacitor? A capacitor is simply an electrical device that is used in storing electric charges. As simple as that. So what do we mean by the capacitance of a capacitor? Capacitance. Capacitance of a capacitor. The capacitance of a capacitor is simply the measure of the ability for a capacitor to store electric charges. And that measure is defined mathematically as C is equals to Q all over V. The capacitance of a capacitor is measured in the units of farad. Farad simply means Michael Faraday. He was the guy that discovered everything about capacitors. And so we honor him in science by naming the SI unit after him. Do you know what I'm saying? So the unit for the capacitance of a capacitor is the farad. The short form of Faraday, Michael Faraday, the farad. Now, there are submultiples of these units. That you have one what? 1 microfarad. You know, we have multiples and submultiples of unit in physics. The decicentimilie micro nanopico. Decicentimilie micro nanopico. So 1 microfarad is simply 10 raised to -6 farad. And this farad is represented with just an F. With just an F. Please take notes. So anytime you see an F in this particular topic, although sometimes we also represent capital F for force, but we are very careful in advanced physics. When we are representing a force, we write F with an arrow on top, telling you that that force is a vector quantity. In this case, we can't write F with an arrow on top. So for this reason, I would love you physics guys over there to writing force, particularly like this. Why you leave F for the farad like that. So 1 microfarad simply means 10 raised to the -6 farad. How about 1 nanofarad? 1 nanofarad. 1 nanofarad is written is the same thing as 10 raised to the -12 farad. So these are the submultiples of the unit of the capacitor. For this one here, it was written 47 microfarad. So this 47 microfarad simply means 47 times 10 raised to -6 farad. You have to take note of what I'm doing because we are going to make use of all this during calculations. We want to quickly look at the symbol for the capacitor. The capacitor has an electrical symbol as follows. The symbol for the capacitor. The capacitor has electrical symbol for a capacitor. You have something like this, something like this. This is the electrical symbol for the capacitor, where these are the terminals. Terminal A, B. The capacitor, of course, has polarities. If you look at this one, this leg is longer than the other leg. The leg that is longer is called the positive leg, and then the shorter one is called what? The negative leg. So a capacitor has polarities. Are we good? So this is the electrical symbol for the capacitor. And I will quickly draw a circuit diagram to include this guy. We may have something like this. Something like this as an electrical symbol for a capacitor. There's an arrow, negative. We'll have a cell here, and then, something like this. So this is your plus, this is your negative. And so this is the capacitor C. The current will flow in this direction and then back to this place. So that is that for that. And you know that I said that the C is equals to Q all over V. You know from the other video I did on current and electricity that Q is equals to IT. So you are free to say that your C is equals to IT all over V. You are free to write it like that. So we are through with what the capacitor is, the capacitance of the capacitor. We're also through with this, the electrical circuit containing capacitor. This is the electrical circuit containing a capacitor. We want to quickly look at arrangement of capacitors in series and in parallel. Anytime I am treating this particular section of the topic, there is what I always do. I quickly do a quick recap on arrangement of resistors in series and in parallel, because that helps us to understand how to go about the arrangement of capacitors in series and in parallel. So let's write. Well, point number 5 and 6. So arrangement of capacitors in series and parallel. Before we understand this subtopic very well, recall that when resistors are arranged in series, they have the same currents flowing through them, but then they have different voltage across. And then let's say this is a resistor, resistor 1, 2, and 3. This is R1, R2, and then R3, all arranged in series. They will have the same electric currents flowing through all of them. Let's suppose this cell connected this. They will all have the same electric currents flowing through them. So how do you have, this is the direction of flow of the electric currents. How do you resolve this resistance to find the combined resistance or the resultant resistance? Very simple. You say that your RT is equal to your R1 plus your R2 plus your R3. That is that for that. And then you're going to have the same voltage. Different voltage across. Different voltage across. The voltage across this, the voltage across R1 is V1, the voltage across R2 is V2, the voltage across R3 is V3. And so from Ohm's law, from V is equal to IR, you're going to have your V1 is equal to IR1, your V2 is equal to IR2, and then your V3 is equal to IR3. Now, let's replicate this in the arrangement of resistors in series. So, capacitors in series. When capacitors are in series, they also have the same electric current flowing through them, but then different, they also have the same electric current flowing through them, the same quantity of electric charge flowing through them, but then different voltage across. This is simply a circuit containing a series arrangement of capacitors. Something like this. I'm gonna draw just 3 of them. Let's suppose that this is our cell. Then this is a closed circuit anyway. So here is your C1, here is your C2, here is your C3. So this circuit, this is a cell. This is the plus side of the circuit, and then the negative side of the circuit. So this is the plus and this is the negative. So the direction of flow of currents will be in this way. The current will flow this way, here, 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 down and back in here. So you're going to have different voltage across. This is V1, this is V2. Sorry, this is V2. This is what? V3. From this point to this point is the voltage across V, and then from this point to this point. So when capacitors are arranged in series as this, you have what? The same quantity of electric currents flowing through them. You have the same quantity of electric current Q flowing through them. And then you have the same current I flowing through them. Very, very important. So from C is equals to Q all over V. We write that the total voltage in the circuit is simply V1 plus V2 plus V3. V1 plus V2 plus V3. That is that for that. And then how do you find the combined capacitance? In this case, the combined capacitance will be added as CT is equals to 1 all over C1 plus 1 all over C2 plus 1 all over what? C3. That is how to go about it. Now, it will interest you to know that the combined capacitance is added as if resistors are what? Connected in parallel. That is one thing you need to know. So from this equation, we can say that our C1 is equals to what? Q over V1. Our C2 equals to what? Q over what? V2. And our C3 equals to what? Q over what? V3. Such that our CT equals to what? Q over what? VT. Our CT equals to what? Q all over VT. So these are the possible equations you are going to have when you have capacitors arranged in series. These equations are very, very important since we are going to make use of them in the next video in our calculations. You know that your Q is equals to IT. So if the time taken for the current to flow through the circuit is given, you are free to say that your C1 is equals to I is equals to IT all over V. Your C2 equals to what? IT all over what? V2. And then your C3 equals to what? IT all over what? V3. So these are the possible equations you are going to encounter during calculations concerning capacitors in series. Take notes, when they are in series, the same current, the same quantity of electric charge will flow through them. But then you have different voltage across. And then this is what you have. We're going to look at arrangement of capacitors in parallel. Capacitors in parallel. Let's look at resistors quickly. Resistors in parallel. How do you go about it? You may have something like this for resistors in parallel. When resistors are in parallel, what do you have? You have the same voltage across all of them. But then you have what? Different currents. You can see that we have I1, I2, I3 here. And then we have V. The current will flow in this direction. you have different currents, but what? The same voltage. Let's look at capacitors in parallel. You may have something like this. This is the symbol for the cell. Plus, negative. The current will flow in this direction. Now let's draw capacitors here. And then let's put another one here. Good. So the current will flow through this way, like this. Then down here, 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 down, down, down. And then back in here. So this is your voltage. When capacitors are in parallel, so this is your C1, this is your C2, this is your C3. When capacitors are in parallel, they have the same voltage but different currents. This I1 Q1. This is I2 Q2. This is what? I3 Q3. I3 Q3. We have I3, Q3. They have the same voltage across, but then they have different currents and what? Different quantity of electric charge. So from C is equals to Q all over V. We write that our C1 will be equal to what? Q1 over what? C1. Q1 all over V. And our C2 will be equal to what? Q2 all over V. And our C3 will be equal to what? Our C3 will be equal to Q all over what? What am I writing? Our C1 will be equal to what? Q1 all over V. Our C2 will be equal to what? Q2 all over V. And now our C3 will be equal to what? Q3 all over V. That is that for that. Do you understand? So the total resistance, I mean capacitance is the circuit, we have CT equals to what? C1 plus C2 plus what? C3. Here what do you have? The total resistance here will what? 1 all over R1 is equal to 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over what? R3. That is that for that. From Ohm's law, V is equal to IR. What do you have? Since we have a common V, we say that our V is equal to what? I1 R2 R1. Your V is equal to what? I2 R3. Your V is equal to what? I3 R3. That is that for that. So that your VT is equal to what? Your IT what? R3 RT. So this is how we go about it in resistors. The reason why I always bring the two when dealing with this topic is that some students sometimes they confuse themselves when it gets to finding the combined capacitance in capacitors when they are in series or in parallel. They will want to add it this way because they believe that they are also in parallel. So when capacitors are in parallel, you add them as if you are adding resistors in series. When capacitors are in series, you add them as if you are adding capacitors what? In parallel. This is a key thing in this topic that you need to know as we proceed. So we are through with this. We want to look at the parallel plate capacitor and dielectric substance. I hope I can clean this. Look at it very well before I move on. So we want to look at the parallel plate capacitors and dielectric materials. That is item number 7. Parallel plate capacitor and dielectric substance. Let me draw something like this quickly. This is a plate, and this is another plate. Connected to a cell of EMF. Yeah, the plus, negative. So you have plus, plus, negative, negative. This is the quantity of electric charges here and also here. So this is your C. You can just write your C. Yeah, your C. Good. Well, let me just clean this out. Yeah. So this is your capacitor. The current will flow in this direction, back and back in here. So this is a picture of a parallel plate capacitor. Now, for a parallel plate capacitor, the plates are separated by a distance d. Please take note of everything I'm doing. And in between this space, there's what we call the dielectric substance. The dielectric substance is that substance that is placed in between the plates of a parallel plate capacitor. It acts like an insulating material. Please take note. They will ask you, what do you mean by a dielectric substance? You can tell the examiners the dielectric substance is simply that substance that behaves like an insulator that is placed in between the parallel plate capacitor. So we may do something like this to represent our dielectric substance or dielectric material. So we can call this the dielectric, we can call this the dielectric substance. The dielectric substance. The whole of this, the dielectric substance. And then, you know, these plates, they also have areas. This plate has what? Area. Take note of this thing I'm saying here. These plates, they also have areas. How wide the plates are. Are they as wide as this book? That is the area of the plates. Now, what to look at? So, in between these plates, when we connect this to a cell, an electric field will be generated in this direction. And there will be arrows pointing from plus to negative, plus to negative. This is the direction of the electric field, E. That is that for that. The direction of the electric field will be from this wing to the other wing. Now, I said something. This plate also has what we call permittivity. The permittivity of this plate is written as something like this. Permittivity of free space. There's what we call permittivity of free space in between these plates because there's a space here. And then the plates that are made with a particular material, we call it permittivity of the material. That is that for that. So we write that the capacitance C of a parallel plate capacitor is directly proportional to the area. Is directly proportional to the area and then inversely proportional to the distance between the plates. What does this mean? It means that the increase in the area of the plate will increase the capacitance of what? A dielectric what? Substance. We increase the capacitance of what? A parallel plate capacitor. And the decrease in the distance will also cause what? The increase in the capacitance of a parallel plate capacitor. It means that if you want to construct a capacitor that has high ability to store electric charge, you are going to make the distance between the plates to be very small, and you are going to increase the area of the plate to be what? Very wide. In that, you're going to have a capacitor with high ability to store electric currents. So removing the sign, we can say that our C is equal to what? All over D. That is that for that. So it means that it is directly proportional to the permittivity of free space, absolute naught, permittivity of the material, absolute R, and permittivity, and also area of the plates. Increase, increase, decrease, 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 increase, increase, decrease. That is the relationship. To this we have come to the end of this particular video, and when next we meet, we shall continue with the energy stored in the capacitor and also the applications of capacitors and also the calculations in this topic. Thank you and God bless you. Don't forget to subscribe, like this video, and share to those that need it. Bye bye. God bless you.